So in today's class, we are going to study about the different methods of excitation in DC generators. We classified the DC generators according to the way in which their fields are excited. Especially, we classified them into separately excited DC generators and self-excited DC generators. So, separately excited DC generators are nothing but those whose field magnets are energized from independent external DC source of DC current. That is nothing but we are supplying an additional independent external DC source. Especially we will be providing battery as a external DC source to these separately excited generators. And self-excited DC generators are those whose field magnets are energized by the current produced by the generator themselves. That is, their magnets, field magnet or winding is supplied current from the output of the generator itself. That is called self-excited generators. So the self-excited generators are again classified into three types. What are they? They are shunt wound generators, series wound DC generators, and compound wound DC generators. We will be moving into details of these three types. Shunt wound means the field windings are connected in parallel with the armature windings, or armature conductors are connected in parallel with the field winding. Then that type of winding or excitation we will be calling it as shunt wound DC generators. The next one would be series wound DC generators. Here the field windings are connected in series with the armature windings. And in compound generators, there will be two field windings. One will be parallel or shunt connected field winding, and another will be series connected field winding. We can see each one in detail. So this is the first diagram. That is, the first diagram represents the separately excited DC generator. So in this this is our separately excited DC generator. In this diagram itself, it is very clear that we will be providing an external DC source. This is our external DC source we will be providing for this field winding. So before going to the detail, first we want to know the electrical symbol of each one. So this is the symbol of field winding RF, and this is the symbol of armature conductors. We will be representing this in term. In this diagram, these two are the main parts of DC generator, right? So in this diagram, it is very clear that the field windings are excited separately using an external DC supply. Normally it is be battery source. And in self-excited, there are three classifications as we already told: series wound, shunt wound, and compound wound DC generators. As the name suggests, the series wound DC generator is nothing but the field winding and the armature are connected in series. And in shunt wound DC generator, the field and the armature windings are connected in parallel. And in compound wound DC generators, we told that there will be two field windings. You can see these two field windings. One will be shunt field winding and another will be series field winding. And in compound wound DC generators, it is again classified into two types, that is long shunt and short shunt compound wound DC generators. In long shunt DC compound wound generators, we can see that the armature, that is armature and the series field winding is connected parallel with the shunt field winding. That is, we can say that the combination of series connection of armature and the series field winding is fully parallel with the shunt field winding. Then that type of winding we will be calling it as long shunt compound wound DC generator. In the case of short shunt DC generators, the shunt field winding will be parallel only with the armature, not with the series field winding. So this shunt field winding will be only parallel with the armature, and this combination will be series with this series field winding. That is, the armature and the shunt field winding will be parallel, and that combination will be series with the series field winding. If it is like this, we will be calling it as short shunt compound DC generators. We will be moving on to in detail about each one. You can see here, the first one will be separately excited DC generator. In this diagram, it is very clear that we will be mentioning some of the currents and the load voltages, etc. You can see here IA. You can see here IA is the, what is IA? IA is the armature current developed from the armature, developed in the armature, and IF is the field current and IL is the load current. Okay, so these are the three currents what we have to mention in this diagram. Then you can see here EG. EG is the generated EMF in the armature, because since it is a DC generator, the output will be external load, will the providing the electrical supply, right? So that electrical power generated in the armature will be calling it as EG, and the load voltage we will be mentioning as the V. Okay, so here we have to write the current equation, voltage equation, power developed in the armature and power delivered to load. So the first one will be armature current. Since load and the armature are connected in series, we can say that IA and IL both are equal, right? Hope it is clear. So the next one will be the terminal voltage. What will be the terminal voltage? We can apply Kirchhoff's voltage law to this circuit. We can say that the algebraic sum of the voltages and the potential voltage current, resistive drops will be equal to 0, right? So here you can see this EG is the generated power that will be dropping against the in this armature and also in the load, right? So the generated EMF EG will be equal to V plus IARA. So from this we can take the output voltage or load voltage V as EG minus IARA. Hope it is clear. So that is the equation for load voltage. Then power developed in the armature. This is our armature. The power developed will be, as we already know that power is the multiplication of voltage into current, right? So in the armature, that is PA, power, or PG, power generated in the armature, we will be taking the EMF in the generated in the armature multiplied by the armature current. So this is the power generated. This is here. So the power multiplying the generated EMF with armature current, EG into IA, that will be our power generated in the armature or power developed. Then what is the power delivered to load? This is our load, right? So applying power is voltage into current, right? So the output voltage is V and the output current is IL. So the power delivered to load, what will be the value of power delivered to load? V into IL. So these are the four equations we have to remember in each of the DC machines, DC generators. Okay. So next we will be moving on. Hope it is clear. So you have to draw this diagram for separately excited, and you have to mention the voltage equation, current equation, and power delivered to load and power developed. These are the four equations you have to remember in all the DC generators. Next one will be DC shunt generators. So you can see in this diagram, DC shunt generator is nothing but the field winding is connected in parallel with the armature windings, right? So you can see here the field winding and armature winding also mentioned here. Both are connected in parallel. This is our field winding and this is our armature. Both are connected in parallel. And what will be the currents derived in this one? You can see that the armature will be, the generated EMF will be developed in the armature, and from this generated EMF a current IA will be produced, and that IA, if we are applying Kirchhoff's current law KCL at this junction, you can see that there will be two outgoing currents and one entering current. So as per KCL, we can apply entering current is equal to leaving current. Leaving current, there are two leaving currents, IL and ISH. So entering current IA is equal to IL plus ISH. So we will be applying Kirchhoff's current law here, and these are the leaving currents. The arrow shows the leaving currents and this is our entering current. So IL will be splitted into load current and the shunt field current. And one more equation you can mention here. What is the equation for voltage or voltage? What will be the value of voltage V? We know that since these three terminals are connected in parallel, all the voltages in each of the terminal or all the branches. In each branch the voltage will be same. That will be marking it as capital V. This is V and this is V and this is V, right? So if we are considering the shunt current ISH, we have to find this ISH. But ISH, if we are applying Ohm's law here, I is equal to V by R, right? So what will be the value of voltage here? Since all are connected in parallel, the voltage across the shunt field will be capital V. Then what will be the value of resistance here? Since it is shunt, we have to mark it as RSH. So V by RSH will be our shunt current as per Ohm's law. Then what will be the terminal voltage or load equation? This is our voltage, right? So as we already told, this is our generated EMF. From this, if we are considering this IARA drop, the voltage equation will be V is equal to Eg minus IARA. Then as previously we said, this is the generated power in the armature, that is multiplying the voltage generated and current in the armature. Voltage generated is Eg and current is Ia. So Eg into Ia will be our power developed in the armature. And also the power delivered to load, what will be the load power? That is load voltage into load current IL. That is V into IL. That is all about the DC shunt generator equations. Okay. Similarly, we can write the DC series generator voltage equations. Series generator is mentioned here. You can see that in series generator, both the field winding and the armature are connected in series, right? So the current produced in the armature IA will be always equal to ISC. Since both are connected in series, the series current and the armature current are same. Similarly, you can see that the load also connected in series, right? So the load current also will be remain same since both all are in series connection. So we can write it as IA is equal to IL is equal to ISC. Hope it is clear. This is the current equation. And next we'll be moving on to voltage equation of DC series motor. You can see here, this is our terminal voltage capital V. And this is our generated EMF. So this generated EMF will be having drop across the armature considered as IARA, and also there will be a drop across the series field winding, that will be considered as IA into RSC. So if we are considering both the voltage drops, we can say that terminal voltage or load voltage is equal to EG minus IARA minus IA into RSC. So taking into brackets, V is equal to Eg minus Ia into Ra plus RSC. Hope it is clear. So this is the equation for load voltage. Then as usual, power developed in the armature and power delivered to load will be remain constant. There will not be any changes. So power developed in the generator will be Peg into Ia and power delivered to load will be equal to V into IL. Then what is about the compound DC generators? Compound DC generators having both series field winding and the parallel field winding. So first we will be moving on to short shunt compound DC generator. What will be the condition? What will be the, you can see in the diagram, right? So this generated EMF in the armature and this is the armature current. If you are applying Kirchhoff's current law at this junction, you can see that there will be an entering current IA and another two currents are leaving, right? So you can write the equation of IA as IA is equal to IL plus ISH. Okay. Then if we are want to take the equation for current ISH, we already know that this is our EG, right? So this both are connected in parallel. This EG will be acting here also. The EG is equal to V plus IL into RSC, or we can say that EG minus IARA divided by the particular resistance. RSH will be giving the shunt field current. So how we will write the terminal voltage equation? Capital V is equal to EG minus IARA minus IL into RSC. Hope it is clear. Then what will be the power developed in the armature? That is as usual Eg into Ia, and power delivered to load will be V into IL. So that is all about the short shunt compound generator. Next we'll be moving on to long shunt compound DC generator. What is meant by long shunt? The name indicates the same. That is long shunt. The shunt field resistance is parallel both to the series field winding and the armature. Then we'll be calling it as long shunt compound DC generators. So similarly here also we can take the current equation. As we already know, armature current IA is here. If you are applying Kirchhoff's current law at this junction, IA will be split into two, IL and ISH. Right? So we can write KCL. By KCL we can apply IA is equal to IL plus ISH. Then what will be the equation for ISH? As I already told, since all are connected in parallel, this voltage will be equal to this voltage will be equal to this voltage. Ellam parallel, right? So we can write the equation for ISH as the voltage divided by the particular resistance, that is RSH. So ISH is equal to V by RSH. All of you please draw these diagrams and write these equations along with this class. Otherwise it will be very difficult for you to understand. Okay. Then what will be the equation for terminal voltage V? What will be the value of V? As we already know, this is our V, right? That is Eg, and we have to consider the IARA drop, and we have to consider this IA into RSC drop. So Eg minus IARA minus IA into RSC. That will be the load voltage. And as per the already said, power developed will be Eg into Ia, and power delivered to load will be V into IL. There will not be any changes in this one. Hope it is clear. Thank you.